Let's now go through question 1. In this question, we have ester undergoing acid catalyzed hydrolysis in water. Looking at the data provided, there are 2 experiments being conducted. Notice that in each of the experiment, the concentration of HCl is kept constant. The concentration of the ester is monitored over time. So we can plot concentration time graph, concentration of ester time graph using this data. Now to check the accuracy of your answer, you are advised to use a graph paper for plotting. So this is my plotted graph. So we want to use the graph to show that the reaction is first order with respect to the ester, and also to calculate the order of reaction with respect to HCl. Now, do note that if we are trying to find an order with respect to a particular substance, you should only use data with only that concentration of reactant is varied. So, meaning if I want to find the order with respect to ester, you should be using any one of this graph, because over the time, the graph shows change in ester, and within that experiment, my concentration of HCl is kept constant at 0.2 mole per dm cube. If I'm trying to show, calculate the order of reaction with respect to the HCl, in this case, I will need to vary the concentration of HCl. This will mean that I will need both the graph, right? Because both graph will actually show involve different concentration of the HCl. Let's look in detail at how we are going to solve this. So because the data type is a concentration time graph and it's non-linear, so when we have a non-linear graph, we expect the order of reactions to be either first or second. But since we are told that it is first order, we know successive half-life must be a constant when used if you have a ester time graph. So do note that you need to show on the graph that how to read the half-life and show that the successive half-life is approximately constant. So to do this, we can take any of the graph. So the starting concentration is, initial concentration is 0.2 mole per dm cube. So the time taken for my concentration of ester to drop to half, 0.1. This time, if you read, it is around 32 minutes. This will be my first T half. The next T half is the time taken for the concentration to fall from 0.1 to 0.05. So meaning we are looking at this time interval. So if you read from the graph, you will find that my T half 2 is now 31 minutes. So from the graph, with concentration of HCl equals to 0.2 mole per dm cube, since my first T half is 32, second T half is 31 minutes, we can say that the successive half-life are approximately constant, and therefore the order with respect to the ester is 1. Next, to calculate the order of reaction with respect to HCl, so remember we should only be using data with HCl being varied. So we have to use both graphs because each of the graph will involve the different HCl concentration. To ensure that we are using the same initial concentration of the ester, we should be comparing the initial rate. And how do we find the initial rate? We have to find the gradient of the tangent at t equals to 0. So this is the graph. The dotted line shows the tangent to the graph at t equals to 0. Do take note how you draw the tangent. It has to be drawn properly. So if you try to draw it, okay, take look at the part of the graph where t is equals to 0. Try and see this graph as short little straight line. So we're going to try and make sure that we extend this part, okay, of the graph. All right, make sure your ruler just touches the curve. Okay, so once you draw the line, you can now calculate the gradient, which is the change in concentration over the change in time. Now we have the correct tangent line drawn. We can now try and find the initial rate from the gradient of the tangent at t equals to 0. So for the graph, with concentration of HCl equals to 0.1 mole per dm cube, we can see that the change in concentration is 0.2. The change in the time is 96 minutes. So our initial rate is 2.08 times 10 to the power minus 3. The unit must be given. It is mole per dm cube per minute. Next, for the other graph, with concentration of HCl being 0.2, the change in concentration, for the same change in concentration of 0.2, the time taken is actually half of the other, which is around 47 minutes. And doing the calculation, we get this initial rate. Same thing, once again, check that you have the unit for initial rate written correctly. Observing this data, okay, you need to highlight that we are using the same initial concentration of ester, but concentration of HCl is double. The initial rate of the reaction is double. Okay, so therefore we can conclude the order of reaction with respect to HCl is 1. There is a second method that we can use to show that the order of reaction with respect to HCl is first order. So how do you do this? Just very much like how we get T half for earlier on, for the graph with concentration of HCl being 0.2 mole per dm cube. You will do the same for the graph with 0.1 mole per dm cube HCl concentration. So using the initial concentration 0.2, we will have to find the time for concentration of ester to fall from 0.2 to 0.1. And we also need to find the time to fall from 0.1 to 0.05. So from the graph, you can read that the successive T half is the same. So it is 63 minutes. Now, you can't just stop here. You have to explain how you observe from the data what is the order of reaction with respect to HCl. So with the same initial concentration of the ester, our concentration of HCl is double when we compare the two graphs, okay, And when the concentration is double, T half is half. Okay, so 63 divided by 2, that's 31.5. Okay, T half is halved. Now, when T half is half, it means that the time taken for the concentration to fall to half is actually reduced. Okay, the time taken is reduced, so it means that the reaction must be faster, and it is faster by double. So therefore, we can conclude that the order of reaction with respect to HCl is 1. To deduce the rate equation and calculate the rate constant, giving its unit, first, we already have the order with respect to the ester and HCl. We know they are both 1. Okay, so 1 is understood. There's no need to write that. And we're going to calculate the rate constant. So we can use any of the graph. Let's say we are using graph with concentration of HCl being 0.1. Earlier on from part B, we have calculated the initial rate to be 2.08 times 10 to the power of minus 3. Okay, so we can simply substitute this in our rate equation. And the K value can be obtained easily. Now do take note, you will need to derive the unit. Okay, remember what is your K? Your K is rate over the two concentration term. So this means that the unit is going to be mole per dm cube per minute divided by mole per dm cube square. Okay, so once you work out everything, okay, what you will have is the unit in terms of per mole dm cube per minute. There is an alternative method to find the rate constant K using the half-life. So note that we already have the rate equation. Rate equals to K, concentration of the ester times HCl concentration. So notice that our acid is 0.2, but this is also a catalyst and it gets regenerated. Okay, it is a constant during the experiment. So we can simplify our rate equation to look something like this, where it is K prime times concentration of ester, where K prime is K times concentration of HCl, and this is our constant value. So remember, we are looking at the simplified equation is a pseudo first order rate equation, right? So we can look at there is a T half that we can obtain from the graph. Your graph actually show this pseudo first order relationship, right? So T half is ln 2 over K. Now note that the K here is my K prime, okay, as in the simplified pseudo order rate equation. But our actual K is K times HCl concentration. So I can now work out what is my K value. Okay, my K is simply ln 2 over T half times concentration of HCl. And here it is 0.108, and our rate constant K is per mole dm cube per minute. Depending on the methods that you use, your answer may be slightly different, but I think it's okay. What's important is that your method that you use is sound based on the correct concept. All right, now let's look at part D. Why is it not possible to determine the order with respect to water in this experiment? Okay, so remember this reaction is hydrolysis of ester. So there will be a lot of water that is present. In fact, water is the solvent. Now we cannot determine the concentration. Okay, basically the concentration of water will be virtually constant because it is the solvent and it is the present in bulk. So if you can't determine if you cannot vary the concentration of any reactant, you will find that it is not possible to determine the order with respect to this substance. Let's now look at question 4. We have a reaction between propanone and iodine. Iodine in water is brown, therefore we can track iodine using a calorimeter. As iodine gets consumed, its concentration will decrease and therefore its color is going to gradually fade. And this will give us a lower absorbent values from the calorimeter. Now the data provided give us the initial rate obtained when different concentrations of the reactant and the catalyst is used. Now to find the order with respect to, let's say, HCl, we must select data with only the concentration of HCl that's being varied. This means we should be choosing experiment 1 and 2 because we can see that when we change to experiment 2, the concentration of HCl is actually half. As for the rest of the reactant, the concentration remain unchanged. There are 2 ways we can use to show our working and derive the order. You can either use the substitution method or the inspection method. Now, substitution method is basically the mathematical presentation. Do take note, regardless of the method that you are using, the working must clearly show which set of experiments are being used to derive the rate order. So to use the substitution method, okay, we can first define our general rate equations to be rate equals to K times concentrations of the catalyst and the concentrations of all other reactants raised to the order of their respective rate order. So when we are comparing experiment 1 and 2, do take note that because concentration of the propanone and the concentrations of iodine, they are constant, they will not impact the ratio of the rate of experiment 1 and 2. Now rate constant, we will also expect rate constant to be a constant because the experiments are supposed to be carried out under the same temperature. So therefore, we will know that the ratio of rate of reaction 1 to 2 is going to be impacted by the concentration of the HCl only. To solve for n, simply make use of the laws of logarithm. We can simplify and then take log on both sides and be able to solve for n. Do take note that n must be round off to the nearest 0, 1, or 2. Now, although we know that the order of reactions could be fraction or decimals, but in H2 calculations, all right, for the rate order, you will definitely get it in terms of 0, 1, or 2 only. All right, so please round off to nearest 0, 1, or 2 unless stated otherwise in the question. So to conclude, our order of reactions with respect to HCl, N is equals to 1. Now, to determine the order of reactions with respect to the propanone, how are we going to select our data again? So I can't be choosing 1 and 2 again. I can choose, for example, experiment 1 and experiment 3. So in this selection, we see that the concentration of the propanone is actually half when we are carrying out experiment 3. For the rest of the reactant, the concentration remains unchanged. So this will be suitable and appropriate experiment to choose 1 and 3. Now, when comparing experiment 1 and 3, again, we're going to follow the same method, knowing that the ratio of the initial rate of experiment 1 and 3 is going to be dependent on only the propanone, all right, raised to the power of m. So again, we are going to use the law of logarithm to simplify, and then to take log on both sides and work out what is the value of m. Since m is 1.1, we're going to approximate it to whole number 1. And therefore, the order of reaction with respect to propanone m is equals to 1. Now, to find the order with respect to the propanone, can I choose experiment 2 and 3 instead? Because 2 and 3 also has a variation in the concentration of propanone. Now, it is possible in this case, although the concentration of the HCl has changed, all right, but we can still solve for order of reaction with respect to the propanone, because the order, we already know, the order with respect to HCl is 1. So if I am comparing experiment 2 and 3, then I will be taking the ratio of the rate of experiment 2 and 3 equals to the rate of the change in equals to the ratio in the change of the concentration of both HCl as well as the propanone. Okay, but for the HCl, because I already know the order, the rate order is 1, so I can substitute n equals to 1 here, and I will just solve for m. Okay, so mathematically, this can also be determined very easily and solved for m. Next, I would just like to quickly run through the presentation for the inspection method. So if you are using the inspection method, do take note that there are 3 things that you need to state very clearly when you are using this method. So I must see from your description, the experiments being compared, the concentrations that were kept constant, and the change in the concentration as well as initial rate. So in determining the order of reaction with respect to HCl, so I'm comparing experiment 1 and 2. The concentrations of propanone and iodine were kept constant. Now for HCl, it was halved, and the rate of reaction was approximately half. So you need to work out how many times will the concentration and the initial rate will change. Okay. So therefore, since your rate is directly proportional to the concentration of HCl, the reaction is first order with respect to the HCl. For the order of reaction with respect to the propanone, we are comparing experiment 1 and 3, where the HCl and iodine concentrations were kept constant. Propanone was half, and the rate was approximately half. So again, our rate of reaction is directly proportional to the concentration of the propanol. Therefore, it is first order with respect to propanol. To state the rate equation for the reactions, so from our general rate equations, we already know the value of N and M from our calculation in A part 1. You are also given that the order of reaction with respect to the iodine is 0. Therefore, our rate equations will look something like this. Please do not include the iodine because iodine concentration raised to the power of 0, this is equals to 1. Now to calculate the rate constant using the results of experiment 1. The easiest way is to take the rate equations from part 2 and substitute all the values that you can see from the experiment 1, so the initial rate and the respective concentration. Please note that you must use experiment 1 results as stated in the question. Now the unit must be stated, it is in per mole dm cubed per second. Alright, so this is because our rate constant K is actually rate over the two concentration term. So this means in term of the unit, we will check out the unit of a rate, which is mole per dm cubed per second over the concentration, which is mole per dm cubed square. So cancel out the common unit. What we have is per mole dm cubed per second for unit of K. In part 4, to predict the time required for the concentration of propanol in experiment 1 to fall to 2.5 times 10 to the power minus 4. Note that this value is actually half of 5 times 10 to the power minus 4, the original concentration of propanol. Now, so we know we can ignore the iodine concentration in our consideration here because the order of reaction with respect to iodine is 0. Now, next, I would like you to take note that the concentration of the HCl, this value, right, is very, very much larger than the concentration of the propanol. So this will tell us two things, right? Your HCl is actually in large excess, okay? So this is in large excess, as well as we also know that your HCl is a catalyst and it can be regenerated. So since it is in a large excess and it can be regenerated, it is going to be approximately constant during the reaction. Okay. So if this is the case, then we will know that our rate of equation can be simplified into this form. Where my K prime is my original rate constant multiplied by HCl. Okay, this is my new constant value. So if you are referring to the pseudo first order reaction, you can see from the simplified equation, right? This is a pseudo order first order reaction with respect to propanol. My iodine is my HCl is no longer in the simplified rate equation. So the rate appears to vary only with the propanol itself. So since we know we are looking at a pseudo first order reactions, therefore we can use the equation involving the half-life. Remember, T half is equals to ln 2 over K, but here my K should be my K prime, okay? K prime, meaning I should be looking at T half equals to ln 2 over K times HCl concentration. So this is what I have. When I substitute, I'm going to get T half being 31.9 seconds. In the next sections of the question, we are going to look at some graphical data. Right, so from the information, let's read the information first. It tells us that the calorimeter is going to measure the absorbance of lights from the cell containing the reaction mixture. So as the color of my iodine fades over time, less light will be absorbed by the cell. So in another word, when it gets less concentrated, the cell absorbance value will be different, right? So it means that the concentration of my iodine is actually directly proportional to the absorbance value that is measured. Now the experiment, you are told that it's carried out using a large excess of propanone and hydrochloric acid, and we're going to start monitoring until iodine is depleted. So due to the relative concentration, we are going to expect that the concentration of my propanone, okay, because it's in large excess, right, in HCl, we're going to expect it to remain approximately constant throughout the measurements of my iodine, right? So therefore, if you remember my rate equations, originally my rate equations look something like this. This means I am now going to get my rate. I can simplify it, my rate to be approximately equals to K prime, where K prime is simply my K times concentration of HCl and my propanone. Okay, this will be an approximately constant value. So what is this simplified rate equation? It's going to show a pseudo zero order reaction with respect to the iodine. So now let's look at the graph. Okay, you have graph 1, which shows you the change in the absorbance with time. So remember, just now we were looking at iodine being directly proportional to the absorbance value. So we know that higher the absorbance, higher the concentration. So this one, we can think of this as this graph to be equivalent to the graph of iodine concentration versus time. Okay, it's a concentration. We can treat this as a concentration time graph. Now, graph 2 is a calibration curve that shows the relationship between the absorbance of lights and concentration. Okay, so if we look at this part of the graph, it shows that you can see that the change in absorbance is from this is 0.42 to all the way dropping to 0, right? So that is the change in the absorbance value that we see. So if I have a corresponding change from 0 to 4.2, that means from this point to this point, I'm going to see a correspondent, this is going to map to a certain change in concentration. It's going to map to change in concentration from 6.0 to 6.4 times 10 to the power minus 5 mole per dm cube. So once we understand the data, we will now look at how to solve the question. B part 1. Using the graph, I want to calculate the rate in concentration, okay, change in concentration per unit time. All right, so this is the rate that we are supposed to calculate. So remember that our rate is reflected in the concentration time graph. So we should be looking at the change in absorbance over time. Okay. So when we look at the rate from this graph, okay, we can find that rate is equals to the change in concentration, which is 0.42 over the time 15 seconds. Okay. But if I'm going to do this, right, this unit for my rate is going to be in absorbance change per second. So this is not what we want. We have to convert this to the change in concentration of my iodine over time. Okay, so I can make my time the same, 15 seconds. So what happened is I just need to find the corresponding change to the absorbance from 0.42 to 0. What is the corresponding change in the concentration of iodine? Okay. So from my graph over here, the change in 0.42 is mapped from 0 to 6.4 times 10 to the power minus 5. Yeah, so this is what we have. 6.4 times 10 to the power minus 5 over 15 seconds. And working it out, I'm going to get my rate in terms of mole per dm cube per second. In case you're wondering, where does this times 10 to the power minus 5 come from? It's from this part here. Take note the unit. It's not 6.4 mole per dm cube, but it is 6.4 times 10 to the power minus 5 mole per dm cube. Right? This is reflected in the label for my x-axis. Now explain how graph 1 can be shown that the reaction is zero order with respect to iodine. Okay, so going back to your graph 1, looking at it again, remember we have to treat my graph 1 like a graph of concentration of iodine against time. So this means that since this is a linear relationship, so the rate of reactions, right, is actually constant. Okay, so if you look at the rate is actually constant, showing us that change in iodine doesn't change the rate of reaction. So to fully explain this, you must point out the relationship between absorbance and concentration. After all, my graph 1 doesn't show concentration of iodine, so you have to point out the relationship and observe that it is a straight line. So your rate equals to the constant, is equals to constant value, constant gradient. Therefore, as iodine decrease, therefore it is zero order. All right, in the last part here, we are looking at another way to actually monitor the concentration of iodine over time, which is to use the sampling method. Okay, so in sampling method, you have a large reaction mixture. All right, so then you will have to draw out sample. Okay, right, so over at regular time interval. All right, so when you draw out the sample, it's important that you quench, okay, the mixture samples so that the reaction sort of freeze at that moment in time, so that when you do a titration, it will reflect accurately the concentration of iodine at the point of sampling. All right. So you will need a quenching agent to stop or slow down the reaction. So what will be a suitable quenching agent? You can either use chemicals that will react away the catalyst. So these are the two that you can use, sodium carbonate and hydrogen carbonate, to react with HCl, which is our catalyst. Okay. I will not recommend the use of sodium hydroxide. Try not to use this. Okay, now sodium hydroxide, typically quenching agent is used in large excess. So when you have sodium hydroxide, it will make your solutions strongly alkaline, right? So for these reactions, right, it is both acid and base catalyzed. So OH minus from a sodium hydroxide can also catalyze this reaction. So you should not be using it. Okay, so if you know if you are trying to remove an acidic catalyst, try to use carbonate. Okay, the weaker bases, so that will make the overall pH of the solutions close to neutral. If you cannot think of a suitable chemicals to use, then always use ice cold water. Okay, if you quench in ice cold water, the low temperature will remove away the energy, absorb away the energy, and your reaction mixture will simply slow down because the temperature is lower. For the next part, you are also required to identify the titrants. Okay, titrants, simply every time you see that you have iodine, you want to monitor iodine with your titrations, definitely it's going to be thiosulfate, because this is the only titrant that you can use.